Yeah, so welcome back everyone to the AI in Robotics seminar at the University of Toronto. Today we are glad to have Antonio to present his work on learning vision-based high-speed flight. Antonio is a postdoc at the University of California at Berkeley, and he works at the intersection of robotics, computer vision, and neuroscience at BAIR under the supervision of Professor Jitendra Malik. Before that, he got his doctoral degree at ETH at the University of Zurich with the Robotics and Perception Group under the supervision of Professor Davide Scaramuzza. Looking forward to your talk, Antonio, and feel free to take it away.
Good. Thank you very much for the introduction, and welcome everybody to my talk on vision-based high-speed flight. I hope this will be both an opportunity to learn something for the people of you who never encountered this topic, but also I can show some fun videos. So the main question that has driven me throughout my PhD is, what does it take to be as good or even better than human pilots? So human pilots are just amazing. From just an RGB image, so this is their input, like they can fly at extremely high speed in complex environment that they've never seen before, like for example in this video that you've seen that you've seen here. My question has been, how can we put these capabilities into autonomous drones? You might wonder why I want to do this. Well, Agile Flight is actually an important problem. In particular, if you consider the fact that nowadays drones are mainly limited by their battery life, usually 15 minutes to half an hour. And of course, we want to maximize the range, the distance they cover during this half an hour. Well, it turns out that the optimal speed at which you can fly to maximize this range is in the range of 10 meters per second. Of course, it depends a bit on the battery, on the drone type, and so on. But it's actually, something fast. And this is maybe a bit unexpected, in particular if for somebody new to the drone community, but easily to understand. If I'm hovering, I'm just kind of standing still and losing all my battery to fight gravity. Instead, if I'm going too fast, then I'm using too much power to fight drag. And this is something somewhere in the middle, in this experiment, around 10 meters per second for the drone I'll be using throughout my presentation, which will maximize our battery life. And you might think this is something very important for many applications, like, for example, search and rescue, delivery, exploration, and yeah, several of these. But also it raises some fundamental robotics research challenges. And that's why it's also very interesting to study this in academia. From all the range of the robotic pipeline, from perception, planning to control. And so doing so pushes the limit of vision-based navigation. And why is Agile Flight difficult? Well, let me present it to you by showing this video of a professional drone pilot flying at extremely high speed in a drone course. You can see it goes fast and, it has to avoid many things, but that's the frame. If you just stop at 1 second, that's the frame that the pilot sees, like extremely blurred. We cannot extract low-level features in here. We have the edges of this gate that are 3 times as big as the normal gate, like the light are completely blurred. So any low-level feature extraction algorithm would fail here. But that's our input. So that's why it's kind of Agile Flight, vision-based Agile Flight is an extremely complex problem. If we look at the related work on Agile Flight, we'll see that mainly existing methods cluster in two groups. The first one, upright, has achieved very high speed, so already good agility, which could compare to the one of humans, but made quite a lot of assumption, assume a lot of prior knowledge of the environment, like for example, it has been pre-mapped, or some external sensors like GPS or a beacon system, which basically limit the approach to wherever these sensors are available. So not everywhere. On the other side, on the other group are methods that are similar to human pilots, in the sense that they just require an RGB image to work and an inertial measurement, but they actually are much, much less agile. My goal has been to sit down in the top right corner, which means like going extremely fast, faster or even, well, as good or even better than human pilots, but with making no assumption, just using RGB images and inertial sensors. We actually have achieved up to some degree this goal, and we have recently demonstrated very high speed flight in complex environment, achieving speeds which are like comparable or even better than commercial drones. So this is a bit a result teaser of my presentation. This is what I'm gonna present you today. How do we get to this, to an autonomous drone that can fly at extremely high speed in any kind of environment, never seen before, and from just RGB images and inertial measurement. And the nice thing about this is that this system is only trained in simulation. Like, this has never seen a real image in the real world. And I think this is something amazing. It is something that, at least in our group, we did not believe was possible like a couple of years ago. We were really surprised by this working. And the main ingredients, the three main ingredients to make this work are input-output abstractions, big diverse data sets, and tailored algorithm. This is something that, you know, nowadays I stress quite a lot because some people might feel, you know, that robotics is just another problem that people can attack with classic machine learning, but I think this is not the case. Like it's needed quite a lot of domain expertise to design these algorithms that work on real drones or on real robots in general. Good. Let me expand on each of these points in detail. But first, I would like to cover a little bit of basics, in particular for the ones of you that are not familiar with the problem of high-speed flight. Usually, formally, we define a high-speed flight as a discrete time continuous value optimization problem, where the goal is to minimize the expected value over a distribution of states or of trajectory rho, and in function of a time-dependent task tau, and the quadrotor and environment state S. What does this mean? Well, this is basically the expected value over the trajectory of, you might think of it as some form of tracking error, if tau is a trajectory and S is a state, but can also be more general. Tau can be a GPS coordinate where you want to go to, and S might be like the position of yourself and the position of the obstacles that you need to avoid. So this is kind of the formulation. I just want to minimize a cost over my trajectories. What's the important part in here? This is kind of a subtle but very, very important part. It's the fact that our policy pi, which controls the drone, does not have information on S of k, does not know exactly where the drone is, does not know the exact environment state, but it only observes some partial observation through, for example, its camera and its like inertial measurement unit. We have no GPS and no prior knowledge of the environment at all. The traditional robotic approach to solve this problem has been to basically divide the problem into subtasks. and in one way or another, estimate this value S of k of the environment and of the robot. So how does this look like? Well, we have some images going into a perception block, a planning block, and to a control block, which then produce navigation commands. Well, this has worked well, you know, and it's actually at the base of many commercial products. This has some limitations. And in particular, the biggest one, latency, and the fact that errors generally compound throughout this large pipeline. That's why a more recent paradigm which many people are exploring and which I've many explored throughout like my work is a more unified and holistic approach where input observation, like for example the images and the MU sensors, get directly processed from a neural network to produce navigation commands. Now, traditional and end-to-end flight have both advantages and limitations. As I mentioned before, like the traditional approach is sensitive to imperfect perception, generally because like the error compound over the pipeline. And also it has quite a high latency because these blocks are sequential, like you can only start when the previous block is done. But on the other side, like it's usually transparent and easy to interpret and quite engineering friendly. Right, so I mean, it's basically the definition of object-oriented programming, right? Having different classes doing different things. On the other side, end-to-end, as I'll show you throughout this talk, is quite robust to imperfect perception. It's not that much subject to compounding errors, and it has quite a low latency thanks to all the advantages, advances in high-speed like computation of the last few years. The problem is, of course, sample complexity. How do we get the data to collect, to basically train these algorithms? And how can we interpret if things are going well or not? At the back time, but also at deploy time. And this is something I'm going to speak a bit more about today. The main approach which I use to train like my algorithms is imitation learning. I just want to mention this is not the only one. What you could do is also doing reinforcement learning, but this is the thing that basically works the best in my experiments, even though I guess this will probably change in the next few years as reinforcement learning gets better and more robust. But why imitation learning? Well, because we have a lot of cutting-edge navigation, planning, and control algorithm. I don't have to list them. I mean, everybody knows them. But the problem is that these algorithms, to optimally function, really to have kind of their optimal performance, they require access to this S of k, which is kind of the state of the environment and the robot. So what's the solution in here? Well, we train our neural networks to imitate these expert methods. But the neural networks won't take this perfect information like the map, the pose of the robot and the task, but just some onboard information, like, for example, the images, the initial measurement, and the task. But they produce basically the same output. But now let's go back to the question that I raised before, which is, where do we get the data to train those methods, to run this pipeline? And the answer for this is simulation. In simulation, we can get really a huge lot of data, a huge amount of data in a very, very limited time. This is basically the main idea. The data is not perfect, but is abundant. And that's exactly what we need. But how to use this simulation data? Well, here we go with the first of the key ingredients for high-speed flight, which are input-output abstraction. Now, input-output abstraction allows us to do transfer learning between domains, which is between simulation and the real world. So they are quite an important concept. And that's why I would like to kind of formally define it. Well, formal up to some degree. Basically, an abstraction function is a method to reduce the gap between two models or two domains, which can be, for example, the real world in M and the simulation in L. This model differ for mainly two things, like the physics and the observation model. So, for example, the rendering. Now, the abstraction function is something that takes these two models and put them closer together. This actually has a precise mathematical definition, which is usually defined in terms of optimal transport. But I don't want to go much into the mathematical details. I prefer to give a practical example to define this better. So suppose that these are our two domains. Like in simulation, we have a forest, which looks like a forest, but we see it's not real. In the real world, instead, yeah, we have this real forest and it looks completely different, maybe because of the lighting, because, of the kind of texture that we have and so on. Now, the abstraction function, which is task and sensor dependent, is, let's say for us, the depth measurement, right? Which is basically the distance for each pixel to, well, the closest object. Now you see that if we use depth measurement instead of the raw RGB images, the two domains, particularly in this case in the observation space, come closer together because the depth measurement is much less dependent on, for example, the rendering, the lighting, and so on. The depth is always depth. So what does this practically mean? That with our neural networks, instead of feeding raw input observation like images, IMU, and so on, what we feed are some form of mid-level vision task, like I mentioned depth here or optical flow, and instead of the IMU, which is kind of dependent on the temperature and pressures, we can do some form of debiasing and then integrate, and like we basically use mid-level vision to abstract away the domain-specific parts and transform then this mid-level vision part into navigation commands. What's the problem with that? Well, that's not the final solution. And the big problem is that, if we go and actually just apply this idea, we will see this, right? That in simulation, we have a nice RGB image and a perfect depth map. But then, when we go to the real world and then we observe stuff through our real camera, here is, for example, a camera that we use on our drone, the One Real Sense. Well, we'll see that the depth looks quite different, right? We have some artifacts, some discretization effects, some missing pixel. And, if we do this, stuff does not work. And this is something expected. This is the definition in machine learning of out of distribution. Like you basically have two modes that kind of basically behave differently. You cannot expect this to work. And how do you solve this problem? Well, by simulating the sensor. And this is another example of the places where domain knowledge comes to the rescue. Just because we know how the sensors look like, most of the times we build them, or we have a quite good understanding of what's going on. What we do is we put this sensor in simulation. We don't need a very accurate model, but just to mimic more or less the fair cases. For example, to mimic a real sense camera, what we did was mimic a stereo camera. So simulate a stereo frame and then compute with stereo matching a depth observation. And doing this is already enough because we see some of the artifacts of the perception, like for example, missing pixels or some form of discretization effects. So that's the concept of input up through abstractions and how to make it work in the real world. Now let's go to the second key ingredient, which is having diverse data sets. So like big data set with a lot of diversity, both in terms of visual and physics. And well, this is kind of an engineering problem. And the main, basically the best way of doing this is through a good simulator. And I cannot recommend more Flatman. Of course, this is biased opinion, but this is basically the simulator that we used in our lab and developed throughout the years. And we basically designed it exactly for collecting this large amount of big data sets. How does Flatman work? It basically divides the rendering problem, from which it uses a game engine, and the dynamic modeling problem, for which we use our internally developed model of the quadroton, which we got better and better throughout the years. Kind of this coupling allows, to like make simulation very fast, but also kind of quite diverse. Because, the main idea is using this game engine, because now what you can do, you can just go online on this Unity store and download, like for really nothing, like, for $20, you could get very, very complex environments designed by artists, and use those environments for your training and testing. This is kind of really a key ingredient, and a no effort one, like you just download stuff. So this is, for example, how things look like. This is one example of the dataset on which we trained and test. So the forest looks quite realistic, right? I mean, there's a river, there are trees, there are branches around, and so things look quite well. But we could also have like urban environments, again, at no effort at all, like disaster environment, if we want to mimic the case of a search and rescue application. So really everything that we want is very, very easy and quick to get.
Antonio, may I ask a question here?
Yeah, please go ahead.
So you mentioned that you were doing some sort of domain randomization for the training later, if I remember correctly. Is that correct? And if yes, would the training, or have you tried training with something like just using depth maps? I guess, what are the failure cases before you got to domain randomization?
Domain randomization is a way of learning the abstraction function together with the task, right? So what's the problem in there? I did not mention this, I was going a bit quick, but basically the problem is that this is kind of more complex. You give the network a bigger task, learn both the abstraction and kind of the control task, and therefore much less data efficient. So we have done this like in the past, mainly for the problem of drone racing, where we were kind of randomizing a bit of everything, background, floor, light, and so on. This works well. It's just that, it requires so much data to be bootstrapped that, it never achieves that high level performance that we get if we spend, some time to think about a good abstraction and using, passing the network like this abstraction directly. So this is a finding that was confirmed by several groups and by several both robotics and computer vision group. And I think it's also quite nice because it saves a bit the computer vision community, right? Because if we could do everything with domain randomization and so on, why do we need computer vision? We just use RGB images and we're done. But no, it turns out that this mid-level representation that we extract are actually super useful for robotics.
Yeah, thanks.
Nice. Good. So, again, we can collect quite huge data sets in this scenario, and this is, for example, data set that we use for training this high-speed navigation system, which contains 200,000 samples which generally include a stereo image pair from which we extract like this depth map using semi-global matching, the HGM algorithm. We also include the drone state and the position of all obstacles, and for each kind of sample, so like the drone state and an image pair, we provide 10 collision-free trajectories, which we use, to train our system. So, I mean, of course, you could use this for other things, because we provide together as well an obstacle point cloud. We provide like 1,000 of them, because to this environment we add some more objects, like trees or some form of spheres, cylinders. Yeah, basically many objects to make the task more difficult. We provide all of these. In case you find this useful, feel free to download it. So yeah, that's how we collect big data set. We just use game engines. So now we go to the last fundamental ingredients of our high-speed flight system, which are tailored algorithms for the task. Now, what we've basically seen, that a very important thing is to take into account that sensor observation are asynchronous, arrive, at whatever time. In particular, images, or in our case, like depth, arrive no more than 20 Hertz. And while I knew, well, this can arrive at whatever frequency we want, and also our task, which in this case for us is kind of a direction where to fly, well, also that can arrive at whatever time. So what we define is define the frequency that we want and process all information separately. At least, in the first branches, where we extract the main level features and process them through history using temporal convolution. These are the things that we found like to work best. So each of these branches over here is asynchronous and completely independent of the previous one. But then we concatenate like the final representation of each of these branches into a synchronous multi-layer perceptron, which basically works at a constant frequency. Usually this is around 30 to 40 Hertz, and just provides like the latest just uses the latest available information for each branches to produce, in our case of high-speed navigation, multiple futures, multiple trajectories. This is also something very important for us. We noticed that, if we just predict one trajectory where we want to go, things would not work. And this is something understandable, right? Because if we have, I don't know, just a tree in front of us, we have two ways of avoiding it, one right, one left. So yeah, we need to explicitly take care of this for the network to optimally function. So this is kind of our network slide. How our network looks like, and the question is, how do we train it? Well, as I mentioned before, like we use imitation learning. We use we assume at the training time we have a point cloud of the environment, which precise information about all obstacles, and pass this point cloud together with the trajectory, the rotor state, to a form of expert, which we call the privileged expert, which basically does nothing else than like using Metropolis Austin sampling to find the best collision-free trajectory in a receding horizon fashion. Then we take the best trajectories, the top 3, and we imitate them with like our student network in here. Now, what do we do with these trajectories? Well, first of all, we project them into a feasible space, which is basically a polynomial fitting, making sure that the drone can actually execute them. And then there are many trajectories, right? Which one do we take? We basically have a decision cost, right? Which basically which depends both on the cost of the trajectory, so how risky it is to take this trajectory, but also has some temporal information, right? So like if at the instant before I was going right, I should continue to go right also now. Then when we decided on which trajectory to take and the trajectory is feasible, we pass this to a form of model predictive control. And the action then goes to our Flatman Simulator that I mentioned before, which we continuously change at every time during training by changing, for example, the density of obstacles, the type of environment, and so on. So like there is, like going back to the question before, there is a form of randomization, but this is not the classic domain randomization in terms of, like images, light quality, background, and so on. It's more randomization in terms at an environment state. So how many obstacles, where the obstacles are, and so on. Good, so we put all of this together, we train our system, and then we deploy it on our drone. This is our drone, in case you're curious. It's extremely simple. It has 2 RealSense cameras in the front, one for tracking, the RealSense D265, and one for depth estimation, RealSense D435 high. And all of our computation happens on board, on the NVIDIA Jetson in here. Like where on the CPU we have our flight stack, and on the GPU instead, like our neural networks runs. Good. So yeah, like with this, we basically I explain you what are the main ingredients, and this is kind of the result. No training at all in the real world, just training in simulation with lot diverse data and abstractions for like very, very high speed in whatever environment like you like. Again, like the drone has really never seen those environments before. It was just put there and given the task of going straight for 40 meters as much as it can, but of course avoiding other obstacles. And we reached very high speed. Like the maximum we got was around 10 meters per second, which is approximately on the range of 40 kilometers per hour. But how does this work quantitatively? Well, we evaluated this, of course, in simulation on the task of going from a point to another point, here in green and in red, while avoiding obstacles. All we are given, is these red trajectories, which it basically connects the 2 points.
And now, the input of this red trajectory is basically just a direction, right?
This is just a direction. Yes, exactly.
Yeah.
Could be, I mean, like in this example is a trajectory, but it could be also, like the straight line between you and a GPS coordinate at, 10 kilometers from you, where you have to go. Right? So, or like the output of a controller, like for example, if there is a user just saying, okay, now I want you to go straight, but the user is not very good, it's not good to avoid obstacle, then the algorithm will take care of the rest.
Yeah.
Good. Yeah, so like basically this is the setup, and we like replicate the setup for like several other methods. Which here, well, I'll explain you what's happening here. This is kind of fast planner, is more this classic kind of pipeline, like, in which you extract the point cloud from observation, then you create a plan using RT star, and then you use this RT star with like, a predictive controller, or like a more reactive one, where basically, you just have your depth map, and then you take the trajectory which kind of fits as lowest probability of collision in form of just your current depth measurement. And we evaluated this on multiple environments and on basically multiple speeds. And we made quite an interesting finding, that is at low speed, like where these methods have been tested and developed, so like 3 to 5 meters per second, things work quite well. And actually at lower speed of 3 meters per second, all of methods work more or less the same. But things do look quite different as we increase the speed, as we reach, speeds of 10 meters per second or higher, where those pipeline methods basically fail for different reasons. Now I'm not going to go into detail of this. But instead, our approach can keep very high success rates, even in these very challenging conditions. Also, we studied what's the effect of noise and latency on our system, and compare this to these existing pipeline methods. What we've seen is that like if we ablate the presence of noise in the observation at deploy time, like our pipeline, our end-to-end pipeline is much more robust like to observation noise. And of course, this makes sense because like we observe this form of noise at training time. So like when this noise will not compound throughout our pipeline. And also another thing that we study is how far are we from the maximum speed, the theoretical maximum speed at which we could fly in this environment. So the theoretical maximum speed is kind of an easy concept, right? It's the kind of the speed at which like you can go maximum before crashing into stuff, and it's something that depends, of course, on your environment configuration. If you have a simplified scenario, this is easy to calculate. For example, just an obstacle in front of you. This is kind of the distance from the obstacle divided the time, your reaction time, which usually includes like three things, like the processing latency, the sensing latency, and the time to actually move. Now, if we compute this maximum speed, like our maximum speed, since we have like a lower like processing latency than others, is higher. So like we can in theory go faster than others. But also more interesting, what we see is that we can fly much closer to the maximum theoretical speed than other methods could do. And again, this is kind of because of our kind of robustness and lower latency. Good. So like we have seen quite good results, both qualitative and quantitative. And one might wonder, so are we done? Do we actually need to do something else? Or can we just, kind of relax? The problem is solved. Well, it turns out that, there are still many problems that we have to solve. And one of the things that, that I really don't like is that, robots, most of the times, they don't learn. Like, they just crash. This is something, just because, like, robots do not, how can I say, like, they cannot interact with the environment and gain knowledge from it. Like, we just have this fixed training time and deploy time. And like, this is something that's not happening in nature. Like in nature, we have a completely different paradigm where every sample in agencies is a test sample. We are always, under exam. And either we cope with like this test sample or we just perish. Right? There's no other way. So the big question is, how can we efficiently learn from this mistake and, always improve in time? Of course, doing something like this is challenging because, we don't want to break drones all the time. We don't want to break robots all the time. So safety is absolutely important. And so we need mechanism to improve robustness and detect ahead of time if something is going to go bad. I worked a little bit into this direction. So basically, I've developed a system for uncertainty quantification in deep learning. And yeah, I mean, the main idea is that we cannot blindly trust neural networks. We need to detect when things go bad and make our best to, to cope with it. Going, for example, in a safety mode, if we detect that our network is uncertain about the current situation, due, for example, to a sensor failure. So just to wrap up, I would like to go back to this related work slide and show you where are we. Well, with this work, I hope that I show you that we still didn't reach human performance. So humans are still better than us, but we definitely made a step in that direction. So now we can fly at very high speed with high success rates by using nothing more than like onboard observation. And in the future, I think because of this online learning, we will see well, performance go more into the human part, or maybe even outperforming it. So I hope I made you interested about Agile Flight, and that is kind of a very cool problem, both from the research side and from the application side. And if you like it, I definitely recommend to check out a competition that we are organizing at HighSpeed, where we basically have the exactly same setup that I described before, in which we want to kind of reach a goal by avoiding obstacles. And we do this in two scenarios. First, where you have static environment, another one which you have dynamic environment, so like with different kind of obstacles moving around. I strongly recommend to do this, in particular if you're new to the Agile Flight community, because you can just use our API, on which we worked on it for several years. So it's kind of stable and easy to use. And so like the competition will open this week. So we will open for submissions this week. So definitely check this out. And there is also a nice award, like a Skydio B2, like the value of $2,000 US. So I think it's something quite cool. You have all of this basically for free. And with this, I would like to conclude, and thank you for your attention.
Thank you, Antonio, for the great talk. And then comes to the Q&A section. Any questions from our audience?
Yeah, I have a question. So we kind of have a similar the question that I have is a little bit related, because we have a similar problem in driving, where this type of learning techniques, they start achieving very, very interesting results. Like there are even companies trying to commercialize learning-based driving stacks, not just in perception, but also in planning and control, like if you think about Wave. So what are your thoughts for the case of drones? Like, what do you think needs to be done to go from the learning-based controllers in research to using a variant of learning-based controllers in drone applications?
Good. Yeah. So basically, I think that in the drone scenario, like this transformation is already taking place. Mm-hmm. And maybe this will go up a little bit faster than autonomous cars, just because safety is important, but not on the same scale. Like most of the time, if a drone crashes, nothing happens. Not always, but it's more difficult to endanger people. So like companies like Skydio already have like deep learning on the core of their perception system, but like from what of course, like I don't have I didn't have a look at their internal source code, but I know from like basically like chatting with people working there that they are starting integrating like deep learning also for their controller into their controllers. So I guess again in the drone space this will come a bit quicker. What we will need probably to improve is this interpretability and this kind of uncertainty point of things, right? In which, if you're a company, in particular, if you're new to deep learning or you have kind of no deep learning expert in your group, for you it's just a black box. You pass in stuff and you get out stuff. You want to understand a bit more, and you want to kind of have an idea of when things go bad and not. So a lot of research is happening on this right now. I guess we're going to see a lot of improvements on this aspect in the next few years. So I guess this transformation will happen quite soon. into the drone world.
Okay, thanks.
Yeah, any other questions? Yeah, maybe I have one question. So, yeah, I think the performance and results of the sim-to-real framework is pretty good and amazing. I'm just wondering, have you met any failure cases of such sim-to-real framework? Like, for example, like I think the scenarios in your simulation are mostly like natural scenes, like forest or like city scenarios. Have you tested like the algorithms that is trained on simulation in the real world in some like indoor scenes which are different from those from simulation? Will that work?
So basically, I mean, we were never flying indoor, just because, you know, like going at 10 meters per second in a building is not super safe. We mainly tested outside, and yeah, so like we basically got zero-shot performance in all the environments that we observed. Maybe like a failure case was, but on the end, I think it was kind of somehow expected, was, you know, when you know, we had very low light, like, you know, if we would fly like during the night, and you know, like the frame would be like well, not very well exposed, and also kind of the resulting depth map would have, you know, a failure case which is completely different from the one that you would have seen in the real world. So sorry, in simulation. So kind of we saw like a little bit of a performance drop in there. But yeah, this is something that could be kind of, I mean, easily managed. Like you just have to include some night data into your data set. So to answer your question, like I think that sim-to-real works extremely well if you provide enough data. So if you have kind of this very large scale data set, which you collect over many kind of scenarios by, you know, randomizing the kind of obstacles, their position and so on, then like things go well. Like then wherever you apply it, as long as you are in the conditions that you simulated, is gonna work.
I see. Yeah, great. Thanks. Yeah, any other questions? Yeah, maybe a follow-up on what I just asked. So for example, you have already very good zero-shot sim-to-real performance. And based on that, if you have you can collect some real-world data for fine-tuning it. What do you think is the most essential ones? Like most essential real-world data that will improve the performance the most? Is that like some failure cases in the real world, or you have some ideas on that?
Yeah. So okay. So like I think the big problem is you know, how to collect this data for fine tuning. You know, when we go into the real world, we cannot make all the assumptions that we make in simulation. Like, you know, we have an exact map of the environment. We always know exactly where the drone is, and we cannot just, you know, try stuff in a reinforcement learning paradigm and see if things work, because we are going to crash the robot all the time. So I think, yeah, a big question is how to, first of all, create learning signal. Where does learning should come from? But a second question, I think, is you know, how basically to change the learning paradigm. I think that, you know, this is the key. Because when we go in simulation, we can use classic machine learning, either imitation or reinforcement learning, in which we want to, minimize a loss. But then when we go to the real world, I think things will be different. This is kind of an hypothesis, but I don't think that we will have to do the same thing. So like collect some data, kind of label it, big loss, low loss, and backpropagate. I think this is more gonna be an association game, in the sense of, this looks like, this is basically what we humans do. This looks like this environment that I've already seen before, and I should behave similarly. And while interacting with the environment, you fine-tune more and more your knowledge. How can I say? A term of nearest neighbor, right? That actually, as humans, we use all the time. Like when we go in a new building, we don't just kind of map the building and then do whatever we have to do. We try to associate this building to our previous knowledge. Am I in a working building? Am I at home? And then try to borrow my previous knowledge from it. And this is kind of extremely quick and extremely efficient. So I guess this is kind of the type of learning that we want to do in the real world.
Yeah, I think that's a really great point. Yes, supervision is like in the real world, and we need some way to quickly transfer the knowledge there. Yes, yeah, thank you very much. Any other questions? If there's no other questions, maybe we can stop here.
Good.
Yeah, thank you very much, Antonio. Thank you for the great talk.
Thanks.
Antonio, thanks so much.